Constructing a numerical frequency distribution requires a few different considerations compared to categorical frequency distributions that we saw in the last video. So first of all, unlike categorical data, numerical data that come from measurements do not naturally lend themselves to classes. Instead, the data must be grouped into classes represented by an interval or a range of value. For instance, you might measure some people having a resting heart rate of 43 beats per minute versus 46 beats per minute. Some other people might have a slightly elevated heart rate at rest, which may be something closer to 67 beats per minute. But in any case, I'm throwing a lot of numbers at you, and we can't really just examine those numbers on their own because that would get very confusing. So we need some way to group those values into values that we say are more similar to each other. Okay, so those are the classes that we're going to construct. And to do this, we're going to go through the process of constructing a grouped frequency distribution to see the process of organizing that numerical data. Okay, so imagine that you're conducting a study on climatology. You collected data representing the record high temperatures for 2023 for each of the 50 states. Okay, so this table below represents those record high temperatures for each of the 50 states in the United States. Okay, in this raw form, it is difficult to make any kind of summary about these data or come to any conclusions about trends geographically in record high temperatures. Okay. So what we want to do is start that process of organizing the data. So the easiest thing that we can do is sort that data. Okay. And what I mean by that is that we want to sort the data in ascending order because it's going to be easier to pick out things like the minimum value and the maximum value of the data set. So in the table below, I have the exact same record high temperatures for each of the 50 states. But now, as you read from top to bottom, left to right, you can see that these data have been organized from smallest to largest. Okay. There are ways to do that in the calculator when you import values into the calculator, and I'll make a video explaining that a little bit more in detail. But if you'll just follow me with the concepts here, it's always really nice to rank your data, list it in ascending order, that is from smallest to largest. So the first step in constructing the classes for our numerical data set is to find the range of the data set. Okay, so the range is going to be the minimum value minus the maximum value. Actually, I have that backwards. It should be the maximum value minus the minimum value. You should be getting a positive number there. Okay. Then what you want to do is find the number of classes desired. Okay. So when you're conducting your own research, you get to make the choice of how many classes you want to organize your data into. And what I mean by that is that we want to sort of create bins where we can place values that are closer to each other. Okay. And you get to make that choice when you're conducting your own research. But when it comes to the homework problems that you're going to see in ALEKS, then that value will be given to you. You don't have to worry about looking for it. Again, it will be given to you. Okay. Then we need to find something called the class width. And that is how wide these intervals or these ranges of values are going to be. The class width is just going to be equal to the range divided by the desired number of classes. Okay. So if the class width is not a whole number, always round up to the nearest whole number. Okay. So if we go back a little bit, we can see from that sorted data set that the minimum value is 100. That is 100 degrees Fahrenheit. And the highest value or the maximum value is 134 degrees Fahrenheit. So if we run through this example for step one, all we need to do to find the range is take that maximum value, which is 134, subtract the minimum value, 100, and we get a range of 34. Then I'm being told to use 7 classes. So to find the class width, we take that range, which is 34, divide it by 7, and we get 4.9. Again, since that's not a whole number, we're just going to automatically round that up to 5. Okay. So be careful here, because the rule for rounding for the class width is always going to be to round up. You might feel tempted if that, for instance, if we had computed 4.4 for the class width, you might be tempted to round down. But we want to just go ahead and round up every time to the next whole number. So if you do get something like 4.2 or 4.3, you will still round that up to 5. Okay. The second step, once we have the class width, is to find the lower class limits. Okay. So the way we're going to start this off is by first using the minimum value as our starting point. And then we're going to create the lower limits of each of our 7 classes. Okay. To do this, all we need to do is simply add the class width to the minimum value, and then continue that process of adding the class width to the next limit that we create until we have the lower limits for 7 of these classes that we're creating. Okay, so if you look at the table to the right, we start off with our minimum value, which was 100, and we're just going to add 5. Again, 5 is the class width that we're using, so we get 105, and then we take that limit that we've created, this lower limit for the second category or the second class, add 5 again, we get the lower limit for the next class, the third class. Okay, then we will add 5 yet again and continue that process until we have a total of 7 classes. So when you go through that process, you should have a lower limit for 7 classes, starting at a lower limit of 100 and then ending at a lower limit of 130. Okay. The third step is going to be to find the upper class limits. Okay. So to find the upper class limits, we need to begin with the lower class limit of the second class. Okay. So let me back up. The second class that we created here had this lower limit of 105. To create the first upper limit, the first upper class limit, all we need to do is take that 105 and subtract 1. Okay. So when we do that, we get 104. And then from that upper class limit, we're going to continue that same process of adding the class width until we have succeeded in getting all of our upper limits for 7 classes. Okay. So again, the second class over here for our lower limits was 105. Okay. So to start off on our upper limit, we just subtract 1 from that. So we're starting at 104. Then we add our class width 5 to get 109, add 5 more to get 114, and so on and so forth until we get our 7th class upper limit, which is 134. Okay, and notice that that last upper class limit is going to be the same as your maximum value from the data set. The fourth step here is going to be to create the class boundaries. The class boundaries are created to close the gaps between class limits. So let's look at this table on the right for a moment. If we inspect the column here that says class limit, our class limits are 100 to 104, okay, 105 to 109, 110 to 114, and so on and so forth, okay. But you notice something here, that if you're thinking about this as a number line, we cover the number 100 all the way to 104, but then we skip to 105, okay? And what I mean by that we've skipped to 105 is that there's a whole range of values between 4 and 5, right? You could get 104.1, 104.2, 104.3, and so on and so forth. So there's a gap between these classes, okay? And we want to make sure that we sort of exhaust the space between the classes so that everything is covered. All of the possible measurement values, even the decimal numbers that are between the whole numbers, are covered by our classes. And so that's what the class boundaries are doing. Okay, so to create our class boundaries, all we're going to do is subtract 0.5 from each of the lower class limits and add 0.5 to each of the upper class limits. Okay, so you can do this one at a time. If you want to start with the lower class limits, we can start there. So again, we'll look at the lower class limit for the first class, 100. If we subtract 0.5, we should be getting a lower class boundary of 99.5. Okay. If we subtract 0.5 from the second lower class limit, okay, we should get the lower class boundary of 104.5. And we can do the same process here. Take the 110, this is the third class lower limit, and subtract 0.5, and we get 109.5. For the upper class boundaries, we're going to look at the upper class limit, so 104, and add 0.5. So if we add 0.5, we get 104.5. Okay. And we can continue that process here, adding 0.5 to the upper class limit. 109 plus 0.5 should give us 109.5. Okay. And notice, now when you're looking at the class boundaries that you've constructed, there are no gaps between them. There is a boundary here between the classes, but there's no gap in between in the way that there was a gap between 104 and 105 where there could be decimal values between them. We've closed the gaps. 104.5 is sort of captured here, so we can think about all of the numbers that might be between 99.5 and 104.5, and then anything that's over that 104.5 will fall into the next bin or the next class based on these next set of boundaries. Okay. So if you continue that process, you should be able to get the class boundaries for all 7 classes, and they should have no gaps, and it should be an exhaustive list of class boundaries. Okay. Now that we've created those classes, all we want to do is count up the data so that we can find the frequency for each class. Like I said, you've taken measurements, and remember the data that we're working with here are the record high temperatures for 50 states. So what we want to do is go through that raw data, and it might be useful to sort that data so that we can sort of count more easily where these values are. Okay. What I mean by that is we want to find all the values of the raw data that fall within each of the class boundaries. So for our first class limit, this first class, we're really looking at values that fall between 99.5 and 104.5. And since we have our raw data listed in order from smallest to largest, then at the top left-hand corner of our data set over here, we can see that there are only 2 values that fall between 99.5 and 104.5. That is the value 100 and the value 104. So we have 2 data values that fall within that class. So the frequency for that class is just 2. Okay. Once you've counted up all the number of data values that fall within each of the class boundaries, you should have this completed frequency distribution table. Okay. So we can see here in the first class, we have a frequency of 2. That means that 2 data values fell between 99.5 and 104.5. 8 data values fell between 104.5 and 109.5. 18 fell between 109.5 and 114.5, and so on and so forth. Okay. But just like with our categorical data distribution tables, we wanted to remember to make sure that the sum of the frequencies is equal to the sample size. Again, if you add up the frequencies in this third column and it doesn't come out to the sample size, that means that you've either undercounted or overcounted some of the raw data. And that can be easy to do because sometimes raw data sets are very large, and counting by hand or counting with your eye leads to some sort of mental strain, and you kind of make an error. Okay, that's very natural to do. So don't beat yourself up if it happens. You always just want to make sure that the sum of your frequencies adds up to your sample size. So in this case, they do add up to the 50 data values that are in this data set, one for each state in the United States. Okay, once we have our frequency, then we can calculate our relative frequencies. Recall that relative frequency is just the percent share of the data set made up by each of the classes. So our relative frequency is going to be the frequency divided by the sample size, represented by the letter n here, times 100. So all we're doing here is taking 2 divided by 50, multiplying that one by 100, and then we're getting 4%. The same thing goes for the second class. We had a frequency of 8 there, so we're dividing 8 by 50, the sample size, and then multiplying that by 100 to get the 16%. Okay, you continue that process until we have all of the relative frequencies represented in our table, and then you can double check that you made no mistakes there by taking the sum of your relative frequencies, because all of those should add up to 100%. Okay, so in all the hustle to construct the class limits and boundaries, count up the frequencies, and calculate relative frequencies, it's easy to forget what we're doing this all for, okay? But using the grouped frequency distribution, we can now answer questions like, how many values in the dataset fall between 2 specified values? Or how many values fall within this class, okay? So for example, we now know that 13 of the record high temperatures recorded for the 50 states in 2023 were between 124.5 and 129.5 degrees Fahrenheit. In other words, 26% of the record highs were within this temperature range. Okay, and we can back up to our frequency distribution table to see this, right? 13 data values fell between 114.5 and 119.5, and that represents 26% of the data. We can also see things like, what is the most frequent class here? And that would just be either the highest frequency value that we find in our table or the highest relative frequency, right? There's a larger percentage of data values that fall in the 109.5 and the 114.5 value range, okay? So there's a lot of things we can do now that the data has been organized. We can summarize it a little bit more clearly than when we first started with our raw data set. Okay. So based on the completed frequency distribution table on record high temperatures, we can see a few things. Like the most frequent class is 110 through 114. This means that most of the record high temperatures fall within the range of 109.5 and 114.5 degrees Fahrenheit. That makes up 36% of the data. We can easily pick out those trends or those patterns. We can also kind of see the shape of the distribution, which seems to be skewed to the right. In other words, the higher classes, or the classes that contain the higher data values, have lower frequency, right? We'll talk more about symmetry and skewness of a distribution a little bit later. But like I said, these are kinds of questions that we can ask the data now and get answers to more easily because we've converted the data from a raw form into a more organized form, okay? So that's the process that you're going to go through whenever you're trying to construct a grouped data distribution or a grouped frequency distribution from numerical data.